I want to share with you some thoughts on the Fermi paradox, which is something that comes naturally when you study planet formation and you realize that there are a lot of planets around a lot of stars. And in particular, my personal contribution to solving the Fermi paradox would be thoughts about the exponential growth and its implications. You remember there's the distribution of the exoplanets that we know, and of course here there's nothing yet in terms of bodies that would be the same mass as the Earth at 1 astronomical unit from their star. So we do not know for sure how many Earth twins there are in the galaxy. However, we can still make statistics. We do know that 14% of stars have a giant planet. Giant planets are easy to detect. So when we make a survey around 1,000 stars and we find 140 giant planets, it means that 14% of stars do have a giant planet. Which means that the Sun, with its giant planets, is among a minority of stars. But it's not an exception. Giant planets are relatively common, even though they are not the rule. We also know that half the stars do have a planet inside with an orbital period shorter than 100 days. So inside 0.03 astronomical units roughly. Because at short period, it's easy to make a survey again. But more interestingly, from the small number of terrestrial planets we have found in the habitable zone of a star, but considering that they are super hard to find, we know that they are numerous. Because we have looked for them, we have found a few, and we know that we can only find maybe, 10% of them if the conditions are favorable. So they must be abundant. And the number is about 50% of the stars have a terrestrial planet in the habitable zone. This is an estimation because of the uncertainty in the detection, but whether it's 30 or 70% doesn't change the big picture I'm going to expand on. It means that terrestrial planets in the habitable zone of the stars are common, very common. The habitable zone is defined as the distance from the star where the equilibrium temperature of a planet is such that liquid water can be stable at the surface. So not too close, otherwise water would evaporate, not too far, otherwise water would be frozen. There's a band. It depends on the temperature of the star itself, but we can define a habitable zone for any star and then do these statistics. Now let's take a step back, which is something we like to do in astronomy. That's what astronomy helps to do actually, and look at this chronology of life where you have 5,000 years of human civilization, human history here, from the pyramids through the antique times and man on the moon. And these 5,000 years of civilization represent 1,000th of the 5 million years of evolution of mankind and the Homo species, roughly, which are themselves only 1,000th of the history of the Earth, which is 4.5 billion years. Okay? And all the life forms for most of the part were not so spectacular. And then came dinosaurs, mammals, etc. And in the last 1,000th, Homo erectus, Homo sapiens, Homo habilis, etc. This history of the Earth itself is only 1/3 of the history of the universe, which is 13.7 billion years, and our galaxy, the Milky Way, probably appeared 12 billion years ago. So there has been stars and planets in the galaxy for 3 times as long as the solar system exists. And in that you have 1,000th and 1,000th. Let's have a look also at the chronology of man-made non-terrestrial transportations. It started with the first plane flight in 1906, which was something like 200 meters in a field and then crashed into a barn or something. But 3 years later, Blériot crossed the Channel, then Lindbergh crossed the Atlantic. In 1974, the sound barrier was crossed by an aircraft. 10 years later, we had the first artificial satellite Sputnik. In 1961, we had man in space. But Yuri Gagarin was in low orbit, probably 300 kilometers altitude, if I remember well. 8 years later, we had a man on the moon that is 1,000 times further. And 6 years later, in 1975, Viking landed on Mars, which is another long range compared to the moon. And in 2004, the Cassini spacecraft got in orbit around Saturn, which is 20 times further than Mars. In 2012, Voyager leaves the solar system in the sense that it has reached the heliopause. It has not reached 1 light year yet, but it is on its way. At this pace, by the end of the century, we should conquest the Milky Way. You should not laugh. I did the math. Look at this plot. All the events I mentioned are marked by a cross in year and kilometers crossed in log scale. That's a very nice alignment. You can clearly fit a straight line here, and this straight line corresponds to going 10 times further every 10 years, or 3 times further every 2 years if you prefer. And if you extrapolate it, you reach the Milky Way diameter by the end of the century. You do. So that's the thing, the basis for Fermi's paradox. We have about 100 billion terrestrial planets in the Milky Way because 50% of stars have one, and there are 200 billion stars in the Milky Way. We realize that the Earth arrives late in the history of the Milky Way, and our civilization itself arrives super late in the history of the Earth. And we're about to conquer the stars in a snapshot on the universe clock. Why hasn't anyone done it before us? Where are they? That's the exact terms of Fermi's paradox. Where are they? Said Enrico Fermi when he did the math for the first time and realized that it's impossible. 1 century is so much nothing. It's enough that a planet forms not 4.5 billion years ago, but 4.500000001 billion years ago, and they have 1 century. They are 1 century ahead of us. Or it's enough that whatever event that led to the development of an intelligent form of life happened 1 century earlier on this planet, and they should already be there. So there are many types of solutions to Fermi's paradox. One of them is, of course, to say that there is no paradox. The ETs, extraterrestrial forms of life, have already come. They are here, or they have come and seen us. But, well, I don't think the extraterrestrials would just come, make a small picture in the air and then fly away, or make a cross, how do we call this, in the field, these rounds in the field, right? Just for fun, and then it was just a joke. No. You can also say, like Calvin and Hobbes, that sometimes I think the surest sign that intelligent life exists elsewhere in the universe is that none of us has tried to contact us. Sure, it can work, but it's not so satisfactory. The other possibility is that actually the ETs don't exist, and that there is some type of great filter behind us, which means something that blocks the evolution between a habitable terrestrial planet and an intelligent form of life which is able to build rockets and leave its planet. It would mean that there are some steps which are necessary to go from prebiotic chemistry to us, which at some point needs some conditions that are very, very rarely met. And you are here at the school on astrobiology, exobiology, so I'm not going to expand on this. You will learn a lot about that. There are indeed specific conditions that are needed that are not necessarily met everywhere. But if that is true, it means that we are the only winners of the cosmic lottery, which could be true, but still is not so satisfactory. On the other hand, there has to be a winner if there is a lottery, but it could also be that such a lottery would have no winner. Why would it have only one? Why not 2, 3, 4? Why not 0? It's not so satisfactory, I find. So the other possibility is that there has been extraterrestrial form of life on other planets, but there is a great filter which is not behind us, but ahead of us, between our state and the conquest of the Milky Way. Because apparently, it's hard to conquer the Milky Way. So if it's easy to become an intelligent form of life, the great filter is ahead of us. One of them, probably you thought of it, is the limit of the speed of light. Did you believe that we could conquer the Milky Way, which is 100,000 light years in diameter, in less than 100 years? No, it would take at least 100,000 years, because physics tells us it is impossible to go faster than the speed of light. Going faster than the speed of sound was a technical problem that we have solved. Going faster than the speed of light is just a limit, not possible. Okay, say we go at 10% of the speed of light. That's easy. Then it takes 1 million years to conquer the Milky Way, which is still nothing on the clock of the universe. So the paradox remains. But it also already shows that there are some limits. And I think that there are various limits to development that may be the great filter. And the one I want to focus on is just the exponential, the dynamics of the exponential. This is a joke I received 3 years ago on internet. The time spent at looking at exponential graphs has increased exponentially in early 2020. Of course, back then it was not funny because it was the number of deaths of COVID-19, you certainly remember, which was a very good example of an exponential propagation of something. One person can contaminate 3 persons, who can contaminate 3 persons, etc. But in terms of, if we get back to space travel, we had this exponential behavior, which appears linear in a logarithmic scale on the y-axis. So the distance traveled as a function of time grows as 10 to the power t over 10. Every 10 years, we go 10 times further. It is equivalent to doubling every 3 years, so 2 to the power t over 3. And it's equivalent to exponential of t over 4.34. That's exactly the same formula. Just to say that when we speak of exponential, it can be given as powers of 2, powers of 10, or the proper exponential function. And similarly, when you talk of a percentage, say something grows by p% per year, it's equivalent to it to be in 2 to the power t over p over 70. In other words, something that grows by p% per year has a doubling time of p over 70. Okay? So if we have an inflation of 5%, it means that the prices double in 70 over 5, that is 14 years. That's what it means. And I think it's easier to talk of doubling times and multiplicating things by 2. So we will all convert in doubling time for now, and you will see how important it is and how it helps. The most famous example is the case of the lily pad on a pond. Okay, you have example here of water. A lily pad doubles the number of its leaves every day, so it has a doubling time of 24 hours. That means every night, from one leaf, there's a branch emerging and a new leaf forming the day after. It's a classical tale. In 30 days, it covers half of the pond, like on this picture. So how long does it need to cover the entire pond? 31, of course. You're not falling into the trap of thinking in a linear growth. In a linear growth, if you take 30 days to cover half, you need another 30 days to cover the other half. In an exponential growth, it's just one step, so one more day. So you knew that. What you may not know is that in less than 2 months, it would cover the entire Earth. The whole surface of the Earth can be covered in less than 2 days at this pace. Less than 2 months, sorry. Easily, whatever the size of the lily pad and of the pond initially. So it goes really fast. Another example is the legend of the inventor of chess. So the king Belkib was bored and wanted an occupation, and Sisa invented the game of chess. So the king was amazed by this fantastic game with so many possibilities and wanted to give him a reward. And Sisa said, oh, I'm just a humble peasant, so I would be happy with just 1 grain of rice on the first square of the chessboard, 2 on the second square, 4 on the third square, 8 on the fourth, and so on. Let's keep counting. After 8, 16, 32, 64 times 2, 121, 228, sorry, times 2, 256, 512. Then we get to 1024. Then
2048.
right.
So 4000.
Yes. Do you start getting nervous at the end? You better get nervous. That's what we get on the 64th square, a number I can hardly read. It's about 10 billions grains, just on one chessboard, multiplying by 2 every time. It represents 50 times the yearly world rice production today. Other example, you take a simple sheet of paper. You may have one here. You fold it in two. The thickness of a sheet of paper is about a tenth of a millimeter. You fold it in two, it doubles. You fold it in two, it doubles again. It becomes thicker, etc. And you can play the game to ask how thick will it be after 10 folds, and you will never get to 10 folds. Try it later. It's super hard to fold a sheet of paper more than 7 times. And it is good because if you could fold it 42 times, the thickness would be the Earth-Moon distance. Yes? 2 to the power 42 times 0.1 millimeter is about 400,000 kilometers. Just 42 times. It is extremely fast. So it's important to realize that the exponential is a very natural function because it's just when something grows proportionally to its present value. So it's coming from the easiest differential equation you can imagine. Y prime is a times y, or y divided by tau, same thing. It corresponds to everything that works on percentage, on a doubling time, on powers of 10, so we find it everywhere. And we find that it's impossible for the lily pad to keep growing. When it fills the pond, there's no more room for new leaves. We find it's impossible to provide the rice. We find it's impossible to fold the paper more than 7 times. So exponential processes do quickly reach their limits. And it's really important to realize that. And in particular, this illustrates how the limit is reached very abruptly. When we started doubling, it was easy, but then suddenly it becomes impossible. It's the same when you fold a sheet of paper. It's easy, and suddenly you can't do it anymore. This illustrates this. These vertical bars represent 100 of whatever quantity that is available. Name it resources, name it pollution you can emit, name it money on your bank account, whatever. There's 100, and it's represented by 1,000 pixels. At first, I take 1 pixel, so 1,000 in red here, and what is still available is shown in green. I double what I take, what remains doesn't care. I double what I take, I double what I take, I double what I take, it does not make a significant change to what remains. I keep doing that, and when I keep doubling what I take, at some point what remains still starts feeling a difference, but from the penultimate to the last but one here, you have a significant drop in what remains, which is losing about a third of its value, while I was still doubling what I take. I double once more, there's nothing left. So suddenly, the behavior of what remains changes drastically from negligible variation to nothing, while the behavior of what I take did not change. I kept doubling. So you can keep doubling for a long while until you reach a limit. And you reach it very abruptly. What does it tell us? Well, we are in an exponential process. The economic growth corresponds to the world GDP, or gross domestic product, the total amount of wealth produced on the world, doubles every 17 years roughly. You can compare the data with an exponential curve and it fits very nicely. The data here stops at year 2000, but when the world GDP was about $40,000 billion, it's now 84, so we have kept doubling in 17 years. Which means we have produced now more wealth in the 21st century than in whole history up to year 2000. Because every step represents as much as everything that was before when you double. It is amazing. Since year 2000, we have produced more wealth than in the whole history of mankind. I checked the number. If it had always been so, with the GDP growing exponentially at that rate, which corresponds to multiply by 40 every century, for instance, you can find a ridiculously small world GDP in the Middle Ages and something absolutely negligible in antique times, when we were building so beautiful things like the cathedrals. At the time of the cathedral construction, the world GDP would have been $6. It does not make sense. So it shows that growth is actually a recent phenomenon. It started with the Industrial Revolution in the 19th century, and before that, the human civilizations had a linear evolution, not an exponential growth. Only the Industrial Revolution permits the exponential growth. So we do not know how long such a recent phenomenon can last. And a problem is that growth goes with CO2 emissions. It has always gone so. And this shows the variations of the CO2 rate in the atmosphere measured in ice for the last 500,000 years. You can see the natural variations that operate on geological times with warm periods and cold periods. And it varies naturally between 180 and 280 ppm in the atmosphere. After the last ice age, we got a more temperate climate. This corresponds exactly to the glaciers from the Alps going all the way to Lyon, and our ancestors here hunting for mammoth, woolen mammoth, the very cold climate, to the climate we had in the Middle Ages, for instance, and in the antique times. And since the Industrial Revolution, we've emitted that much carbon dioxide in the atmosphere. So that's a very significant quantity, more than the difference between warm times and ice ages, that we have emitted in a time that is much smaller than the thickness of the line. So clearly not a natural variation, clearly us. The problem with that is that we are in an exponential dynamics. So it took us 2 centuries to add 120 ppm of CO2 in the atmosphere. If we keep going with growth, it will take us 17 years to add 120. Because we are now producing so much wealth and using so much energy that it corresponds to what we have done since now. Which means 500 ppm tomorrow, and then 17 years later, twice that. So we skyrocket and just no way. Because CO2 is a greenhouse gas, as you know. So the change of CO2 in the atmosphere changes the climate. I don't need to describe this to you, I think. But we see that we have a problem because this economic growth, which is cool and allows us to have a very comfortable life, goes with CO2 emissions. So what we have done so far is emit CO2, which corresponds to locking ourselves inside a greenhouse. That's equivalent to that. We have built a greenhouse around our planet. As you know, if you put a greenhouse on your tomato field, the temperature doesn't immediately rise. It needs some time for the heat of the sun to accumulate and the greenhouse to produce its effect. That's where we are now. But if we keep with growth, what we are doing is we double the thickness of the greenhouse now. And we keep building greenhouses to pile up. This must stop for obvious reasons of survivability and having a pleasant climate. How can we stop? We want to reduce our CO2 emissions, but we like being rich. So we would like to go on with economic growth without emitting CO2. The key is that producing wealth requires energy. That's the thing you need. You need to transform some material that is worthless into something that is precious, and for that you need energy. It also works it's also true if you just work in an office. I'm not producing anything material, but I need energy to run my simulations to produce knowledge. And I need a computer and a heated office. You need energy. So the solution may be renewable energies. This is the distribution of the energy consumption with time. As you can see, it follows the exponential curve corresponding to the GDP. But what you can see is that mainly, like 90% of the energy we use in the world is coal, crude oil, natural gas, and traditional biofuel, so emitting CO2. So if we want to move to renewable energies, it means we need to transform all that with this. in a few years. Good luck. It's not going to be easy, but let's admit we do it. I've taken the number of the world consumption of energy 10 years ago. That was 5.67 times 10 to the 5 joules, or 150,000 terawatt-hours. Who cares? Terawatt-hours. If we keep with 2% growth per year, which is the average growth of our energy consumption since the 90s, it means that in 463 years, which is the time between Henry II, King of France in the Renaissance, and now, we would need all the energy received on Earth from the sun. Which means if you want to use renewable energy, at this time, you will have to have covered the entire planet with solar panels of ideal efficiency. Little problem, because there's no room left to grow food, you know. Let's admit we can do it. 1,100 years later, we would need all the energy emitted by the sun in all the directions. And that's the time that's between us and Clovis, who founded the Kingdom of France. So if you want France to live for as long as it has already existed and keep growing in energy, you need to be ready to prepare for encircling the sun. Covering the sun is what science fiction authors often call a Dyson Sphere, which is catching all the energy emitted by the star and bringing back this energy to Earth. Sure, let's do it. But at this pace where we grow our energy consumption by 2% per year, 35 years later, we need another star. 35 years later, we need 2 more stars. In less than 2,000 years, we would need all the stars of the galaxy. 2,000 years only. Little problem. So it's actually impossible to keep growing exponentially our energy consumption. Just impossible. If you want your country to last for a few centuries. And that may be the solution to Fermi's paradox. In the end, if an indefinite exponential growth was possible, some extraterrestrials would already be here. Because there's no reason for us to be the first ones, while actually there are billions of habitable terrestrial planets. So either extraterrestrial forms of life have appeared, have tried to conquer the galaxy, and have eventually destroyed their planet or exhausted their resources and collapsed. Or extraterrestrial forms of life have developed on other planets, realized that an exponential growth was not something to pursue, and they have stopped about that and gave up space conquest, and they are peacefully on their planet in a sustainable way. And we will never see them and never hear of them. But what we see here is that growing until conquering the Milky Way, which would be around 2080 if we keep this exponential growth, is truly impossible. Otherwise, ETs would be here teaching to you how to do, instead of me teaching to you how not to do it. So I don't know for the past about great filters, but I can tell you there's a great filter ahead for sure. And I think it's important to realize that. And eventually, what's the conclusion? Well, sobriety is the only solution. We must reduce our greenhouse gases emissions now, which means we must reduce our energy consumption, which implies that we must reduce the amount of wealth produced because we have never found a way of producing wealth without consuming energy. So something like green growth or sustainable development, I'm afraid, are oxymorons and just don't work together. It's just a contradiction. So if we have less wealth produced, we have to think about what to do. I suppose the best way would be to share wealth better, but that's an open debate. The optimistic thing is that with the COVID-19 pandemic, we have proven that we can put health before economy. At least for a short time, we said, okay, cancel everything, stop producing everything, stay at home, stay healthy. We actually have to do it on long term because the exponential growth of the COVID-19 cases and the exponential growth of the CO2 emissions are exactly the same thing, and we are at the same place now as we were just before lockdown in front of the COVID-19, for instance. Which means we must invent a new society and economy without growth. And that's super hard. It's not an astrophysicist who is going to tell you how to do it, but we know it's possible because there has been a lot of civilizations in mankind history without growth. So it is possible. We have so many techniques now that we can certainly live comfortably without growth. But we have to change the whole economic system. And I think it's good to realize that thinking of stars and exoplanets brings us back on Earth. There are billions of planets, but no extraterrestrial form of life has managed to conquer the galaxy. That's fact. At the scale of the universe, at the scale of the Earth, and even at the scale of mankind in general, growth is a very recent and therefore fugitive phenomenon. We do not realize that because our grandparents and the grandparents of our grandparents were raised in a world with growth. And so generation after generation, the conditions of life improved and growth is very natural to us. But it's not. Speak to someone in ancient Egypt or in the Middle Ages, they had no growth. And like every exponential phenomenon, growth is not sustainable. I really insist on that. The exponential dynamics is poorly understood by people in general. And even when I did these numbers, I was amazed. You laughed when I showed you some numbers. And of course, it's amazing how fast exponential growth proceeds. But we really have to realize that it is the way it doubles regularly and that it's not a slow growth. So it has to stop now. And I stop here too. And I'm happy to take questions.